The solar system you learned about in school is missing most of itself. Not a small omission, not a rounding error. The diagrams we grew up with, 8 planets, a thin ring of asteroids, and then emptiness left out an entire zone that stretches for billions of miles, contains billions of objects, and may be home to a world larger than Earth that we have never directly seen. The standard model of our solar system is, at best, incomplete. At worst, it is a dramatic understatement of reality. Beyond Neptune, past the edge of everything familiar, lies a region that planetary scientists are still trying to make sense of. The objects out there are not behaving the way our physics predicted. They are moving in patterns that should not be possible. Some of them are geologically alive, despite sitting at temperatures near absolute zero. Some have ring systems that defy our understanding of gravity. And the recent discovery that the belt itself extends far beyond its supposed outer boundary suggests that we have been mapping the wrong territory entirely. This is the Kuiper Belt, and the more we look at it, the stranger it becomes. To understand what makes this region so remarkable, it helps to first correct a common misunderstanding about its shape and position. Most people who have heard of the Kuiper Belt picture it as a spherical shell wrapping around the entire solar system, a hollow bubble of frozen debris surrounding everything. That description actually fits a different structure called the Oort cloud, which sits far beyond the Kuiper Belt and extends up to 100,000 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, roughly 93 million miles. The Oort cloud is so vast that its outer edge is nearly a quarter of the way to the nearest star. The Kuiper Belt is much closer and much more structured. It is shaped like a torus, what geometers call a donut shape, or more precisely, a thick flattened disk. It aligns almost perfectly with the plane of the planets. If you could view the solar system from the side, with the Sun in the center and the planets strung along a horizontal line, the Kuiper Belt would appear as a wide band, extending outward from Neptune's orbit. It begins roughly 30 astronomical units from the Sun and extends out to approximately 50 astronomical units. That range encompasses an enormous volume of space. For comparison, the asteroid belt between Mars and Jupiter, the ring of rocky debris that most people are more familiar with, is a much narrower, much less massive structure. The Kuiper Belt is roughly 20 times wider than the inner asteroid belt and contains hundreds of times more mass. It is not a thin scatter of rocks. It is a densely populated frontier. The composition of these objects is what makes them scientifically valuable. In the inner solar system, the young sun's heat was intense enough to vaporize ice during the formation of the planets. That is why the asteroid belt is made primarily of rock and metal. The volatile compounds were burned away early, but in the cold dark beyond Neptune, temperatures are low enough that everything freezes solid. The objects of the Kuiper Belt are made of water ice, ammonia ice, and methane ice. Astronomers call these materials volatiles, and at the temperatures of the outer solar system, they become as hard as granite. This means the Kuiper Belt is not a junkyard. It is a deep freeze, a preservation chamber for the original raw materials of the solar system. These objects formed 4.5 billion years ago and have changed almost nothing since. When we study them, we are looking directly at the ingredients that built Earth, Mars, Venus, and every other rocky planet. They are fossils of a formation event that we cannot replay or observe directly in any other way. The belt formed because planet building was not a clean, efficient process. When the Sun ignited at the center of the early solar system, the surrounding disk of gas and dust began clumping into progressively larger bodies. The giant planets Jupiter, Saturn, Uranus, and Neptune grew large enough to gravitationally dominate their neighborhoods, but that domination came at a cost. The process of building these massive worlds left behind enormous quantities of scrap material, debris that was never incorporated into a planet. In the inner solar system, much of this material was eventually swept up by the terrestrial planets or ejected by Jupiter's gravity. In the outer solar system, it had nowhere to go except into the stable region we call the Kuiper Belt. There is also evidence that the belt's current shape was sculpted by the migration of Neptune. Current models of solar system formation suggest that Neptune did not form in its current orbit. It likely formed closer to the Sun and then migrated outward over hundreds of millions of years. As it moved, its gravity acted like a plow, pushing material outward and organizing the scattered debris into the structured ring we observe today. The belt is, in a very real sense, a scar left behind by the youth of the solar system. The first object beyond Pluto that truly forced scientists to rethink their assumptions was a body called Arrokoth, which was visited by the New Horizons spacecraft in January of 2019. New Horizons had previously flown past Pluto in 2015, and after completing that mission controllers redirected the spacecraft further into the Kuiper Belt toward this distant target. Arrokoth sits more than 4 billion miles from Earth. Before the flyby, even the most powerful telescopes could only render it as a single bright point of light against the stars. The images that came back from New Horizons were immediately surprising. Arrokoth is not round. It does not look like a sphere, a potato, or any of the irregular shapes we typically see in asteroids. It looks like two reddish pancakes pressed together at a narrow connection point. One lobe is noticeably larger than the other. The entire structure is flat and elongated in a way that makes it look almost like a squashed snowman lying on its side. Astronomers classify this shape as a contact binary, two separate objects that have merged into one. The shape itself was fascinating, but what it implied about the formation process was even more significant. When Arrokoth formed, there were two dominant theories about how small solar system bodies come together. The first theory, sometimes called the accretional cascade, suggested that objects like Arrokoth form through high-speed collisions. Small rocks smash together at high velocities, shatter into smaller pieces, and those pieces gradually accumulate into larger ones over millions of years. This is a turbulent, violent process. The second theory, which had been gaining mathematical support but lacked physical evidence, was called pebble cloud collapse or streaming instability. In this model, concentrations of dust and pebbles in the early solar nebula gradually self-organize under their own gravity. They collapse inward, slowly and gently, building objects from the bottom up without high-speed collisions. Arrokoth resolved this debate. The connection point between its two lobes, the narrow neck where the two halves meet, is smooth. It shows no cracking, no evidence of a violent impact, no shearing or distortion. If these two lobes had smashed together at speed, the contact zone would be fractured and deformed. Instead, the evidence suggests that the two lobes once orbited each other in a slowly decaying binary system. Over millions of years, the orbit tightened. The two objects drew closer. Eventually, they touched at a relative speed of roughly walking pace, less than 2 kilometers per hour, and fused together gently. The shape we see today reflects that quiet, unhurried merger. Because Arrokoth sits in a cold, quiet corner of the solar system, it has experienced almost no geological activity since the day it formed. There are no volcanoes to resurface it, no atmosphere to erode it, no internal heat to reshape it. Its current form is almost identical to the form it took 4.5 billion years ago. It is the closest thing we have to a direct photograph of the planet-forming process, frozen in time and waiting for a spacecraft to photograph it. The lesson from Arrokoth is that the construction of our solar system was, at its most fundamental level, a gentle process. The building blocks of planets did not begin with catastrophic collisions. They began with slow accumulations, quiet drifts, and patient mergers across enormous spans of time. Earth itself, and every other rocky world, traces its origin back to a process that looked more like snowflakes settling than boulders crashing. But gentle formation is only one face of the Kuiper Belt. Other objects in this region have histories that are anything but quiet. Haumea is a dwarf planet that sits in the same neighborhood as Arrokoth and Pluto, but it could not look more different. Where Arrokoth is quiet and unchanged, Haumea is a world that has been violently deformed and continues to bear the marks of a catastrophic ancient event. Its most immediately striking feature is its shape. Haumea is not even close to spherical. It is elongated, shaped roughly like a rugby ball or a somewhat flattened egg. Among objects of its size in the solar system, nothing else looks like it. The reason for this shape is rotation. Haumea spins extraordinarily fast. A full day on Earth takes 24 hours. A full rotation on Haumea takes less than 4 hours. This rate of spin is so extreme that centrifugal forces, the outward push generated by rotation, have physically distorted the planet. The equatorial regions are being flung outward, stretching the planet along that axis. while the poles are being compressed inward. The planet has been sculpted into its egg shape by its own momentum. If Haumea's rotation were even slightly faster, the centrifugal forces would overcome gravity entirely, and the planet would begin to shed material into space, potentially tearing itself apart. Haumea is, in a sense, spinning at the edge of its own structural limit. The source of this rapid rotation is almost certainly a massive collision. Something large struck Haumea billions of years ago, transferring angular momentum into the planet and sending it into this extraordinary spin. That same collision likely scattered debris into space, some of which eventually coalesced into Haumea's two known moons, Hi'iaka and Namaka, and possibly contributed to a thin ring system that was discovered around the planet in 2017. That ring system, while remarkable, is less confusing than the ring discovered around another Kuiper Belt object called Quaoar. Quaoar is roughly half the diameter of Pluto, a modest-sized dwarf planet that, until recently, attracted little scientific attention. In 2023, astronomers announced that Quaoar has a ring. This alone would not be unusual. Rings have been found around several unexpected objects in recent years. What made this discovery remarkable was where the ring is located. Planetary rings exist because of a fundamental gravitational boundary called the Roche limit. This limit describes the distance from a planet within which tidal gravitational forces are strong enough to prevent material from clumping together. Inside the Roche limit, gravity tears material apart rather than allowing it to accumulate. This is why rings exist. Where they do, the material cannot coalesce into a moon, so it remains as a ring. Outside the Roche limit, the opposite happens. Material tends to clump together under its own gravity and eventually builds a moon. The boundary between these two behaviors is the Roche limit, and it is a precise calculation that depends on the density and mass of the central body. Quaoar's ring is located at a distance roughly 7 times the planet's own radius. This is far outside where the Roche limit should be. According to our standard calculations, the ring material at that distance should have clumped together into a small moon within a matter of decades, not lingered as a stable ring for what appears to be an extended period of time. Yet there the ring sits, stable and intact, defying the model. Scientists have proposed several possible explanations. One idea is that the particles in Quaoar's ring are unusually elastic. When ring particles normally collide, they tend to stick together like wet sand because the collisions are slow and gentle enough for the material to aggregate. If Quaoar's ring particles are more like rubber balls, bouncing off each other rather than sticking, the ring might be able to resist aggregation longer than models predict. But this would require a very unusual material composition. Another hypothesis involves a small, unseen moon just beyond the ring, whose gravitational influence might be shepherding the ring particles and preventing them from spreading or clumping. Similar shepherd moons have been found maintaining the sharp edges of Saturn's rings. Neither explanation has been confirmed. Quaoar's ring remains a genuine anomaly, a structure that our current physics cannot adequately explain. It is a reminder that our models of gravitational dynamics, as sophisticated as they are, may have significant gaps. If Quaoar challenges our understanding of ring mechanics, the dwarf planet Eris challenges our assumption about what a distant, cold world can be. Eris was discovered in 2005 by astronomer Mike Brown and his team at the Palomar Observatory. At the time, it appeared to be larger than Pluto, which triggered an immediate scientific crisis. If Eris was a planet, then there were other large bodies in the outer solar system that also had a claim to planetary status. The International Astronomical Union convened and ultimately decided to solve the problem by redefining the word planet, creating the new category of dwarf planet and placing both Eris and Pluto within it. More precise measurements later showed that Pluto is slightly larger in diameter, though Eris is significantly more massive. The discovery of Eris directly caused the reclassification of Pluto, a chain of consequences that began with one telescope image. But Eris is interesting for reasons that go well beyond the politics of planetary classification. Eris orbits nearly 6 billion miles from the Sun, roughly 3 times farther than Pluto, and so remote that from its surface, the Sun would appear as little more than a very bright star. At that distance, temperatures on the surface hover near absolute zero, the lowest temperature physically possible. For decades after its discovery, scientists assumed Eris was a geologically dead world, a frozen, inert lump of ice that had not changed since the solar system's infancy. The James Webb Space Telescope has revised that assumption substantially. Webb studied Eris by analyzing the wavelengths of sunlight reflecting off its surface. Different materials reflect light at different wavelengths, allowing astronomers to determine surface composition remotely. What Webb found on Eris was methane ice, and not just any methane ice. There are two isotopic signatures of methane that astronomers can distinguish. Primordial methane has been sitting on the surface since the solar system formed, and its isotopic signature reflects that ancient origin. Fresh methane, produced by recent geological processes, has a different signature that reflects more recent formation. The methane on Eris is fresh. This should not be possible on a dead world. Fresh methane means ongoing chemical processes. It means that something inside Eris is generating the material and venting it to the surface. The leading explanation involves radioactive decay. Even at this distance from the Sun, Eris likely has a rocky core that contains radioactive elements: uranium, thorium, and potassium. As these elements decay over billions of years, they release heat. That heat is enough to maintain a slowly churning interior, possibly including a subsurface ocean of liquid water or a slush of partially melted ice beneath the frozen crust. Pressure from this warm interior gradually builds up and eventually forces material outward through cracks in the crust. Gases and fluids vent to the surface and freeze instantly in the extreme cold, depositing fresh, bright ice that covers older, darker terrain. This process, called cryovolcanism, volcanic activity driven by icy rather than molten materials, explains why Eris is one of the brightest objects in the solar system. It reflects nearly all the sunlight that hits it because its surface is constantly being refreshed by this internal venting. Eris is not a frozen fossil. It is an active world, driven from within, continuously resurfacing itself in the same way that Earth's volcanic activity continuously reshapes our planet's surface. It is geologically alive, 4.5 billion years into its existence, sitting at the edge of the known solar system. The discovery of active geology on Eris has changed how scientists think about cold, distant bodies throughout the solar system and beyond. The assumption that small, remote worlds must be geologically dead is no longer valid. If Eris can sustain internal activity at its extreme distance from the Sun, then similar processes might be occurring on ice-rich worlds in other planetary systems, worlds that astronomers previously dismissed as too cold and too small to be geologically interesting. The implications extend to the question of habitability. A world with internal heat, liquid water beneath its crust, and active chemical cycling is, at least in principle, a world that could support life. Eris is not considered a prime candidate for this. The challenges are enormous, but the fact that it is active at all expands the range of environments that scientists have to consider when thinking about where life might exist. But the individual objects in the Kuiper Belt, remarkable as they are, may not be the most significant discovery to emerge from this region in recent years. For decades, astronomers believed the Kuiper Belt had a distinct outer edge. Starting from Neptune's orbit at 30 astronomical units and moving outward, the density of objects remained high and relatively consistent. But at approximately 50 astronomical units, less than twice Neptune's distance, the population dropped sharply. Objects became dramatically less common. The census of Kuiper Belt bodies seemed to stop at this boundary, as though a wall had been built. Astronomers called this the Kuiper Cliff. The assumption seemed reasonable. Perhaps the gravitational sculpting that created the belt also set a hard outer limit. Perhaps the belt simply ended there. Beyond 50 astronomical units, the thinking went, there was nothing until the Oort cloud began, thousands of astronomical units further out. Then the New Horizons spacecraft kept flying, and it found something unexpected. After completing its flyby of Arrokoth in 2019, New Horizons continued outward into the region beyond the Kuiper Cliff. The spacecraft carries a student-built dust detector called the Venetia-Burney Student Dust Counter. This instrument measures the number of dust particles the spacecraft encounters as it travels through space. The premise is straightforward. If space beyond the Kuiper Cliff were truly empty, the dust hit rate should drop to nearly zero. It did not drop to nearly zero. The dust counter continued registering hits at a rate inconsistent with empty space. Something beyond the Kuiper Cliff was generating debris dust particles produced by collisions or other processes. Whatever was out there was close enough to the Sun to be part of the solar system, but too faint and too distant for standard telescopes to resolve. The confirmation came from a new survey conducted using the Subaru telescope, an 8.2-meter optical infrared telescope located at the summit of Mauna Kea in Hawaii. Using a wide-field camera capable of imaging enormous swaths of sky in a single exposure, astronomers conducted a systematic search of the region beyond the Kuiper Cliff. In late 2024 and into 2025, they announced the discovery of a new population of objects, a cluster of bodies orbiting between 70 and 90 astronomical units from the Sun. These objects are not sitting just beyond the cliff. They are 40 to 60% farther out, occupying a completely separate region of space with a significant gap between them and the main Kuiper Belt. In other words, there appears to be a second Kuiper Belt. The structure of a disk, a gap, and a second outer disk is not unique to our solar system. Astronomers have observed this double disk architecture around other stars. The star Fomalhaut, roughly 25 light-years from Earth, is surrounded by a similarly structured debris system, an inner disk, a gap, and an outer ring. Several other nearby stars show comparable patterns when imaged with high-resolution telescopes. The interpretation in those systems is that planetary bodies occupy the gap between the two disks, their gravity clearing out material and maintaining the separation. The discovery that our own solar system has this same double disk structure means that we have been standing inside the inner ring, looking outward and mistaking its edge for the edge of the system. The solar system extends considerably further than we thought, and the gap between the two Kuiper belts suggests that something is maintaining that separation. This brings us to the most consequential mystery in the outer solar system. Among the distant objects that astronomers have cataloged, a small group stands apart. These are sometimes called extreme trans-Neptunian objects, worlds that orbit far beyond the main Kuiper Belt in paths that are dramatically elongated, stretched out into long oval trajectories that take them very far from the Sun and then swing them back in. Their orbits are nothing like the near-circular paths of the planets. They are the most distant and most isolated bodies in the solar system. The first and most puzzling of these was found in 2003. Its formal designation is Sedna, named after the Inuit goddess of the sea. When the discovery team first analyzed Sedna's orbit, they realized immediately that it violated the patterns that govern every other known body in the solar system. Sedna follows an orbit so elongated that it takes approximately 11,400 years to complete a single journey around the Sun. At its farthest point, Sedna travels nearly 900 astronomical units from the Sun deep into the empty darkness between the Kuiper Belt and the Oort cloud. It then sweeps back inward, but only to a point. The closest Sedna ever gets to the Sun is roughly 76 astronomical units. That number, 76 astronomical units, is the critical clue. Every other object in the Kuiper Belt interacts gravitationally with Neptune. When Kuiper Belt objects get too close to Neptune's orbit, Neptune's gravity kicks them into more extreme trajectories. This is a well-understood process, and it explains how many of the scattered objects in the outer Kuiper Belt got their unusual orbits. Neptune acts as a gravitational sculptor, reaching out and redirecting objects that pass too close. But Sedna never gets close to Neptune. Its minimum distance of 76 astronomical units keeps it far outside Neptune's effective gravitational reach. Neptune cannot be responsible for putting Sedna where it is. At the same time, Sedna is not far enough out to feel the gravitational influence of other stars or of the galactic disk. The nearest star system is more than 4 light-years away, more than 260,000 astronomical units, and its gravitational pull at Sedna's distance is vanishingly small. The tidal pull of the Milky Way galaxy itself is likewise too weak to explain Sedna's orbit at this range. Sedna occupies what orbital dynamics specialists call a detached orbit. It sits in a zone where no known force can account for its current position. It could not have formed where it is. There is not enough material at 76 astronomical units to build a world of Sedna's size. It could not have been scattered there by Neptune. It is too close to have been delivered there by the gravity of passing stars. And nothing in our current models explains how it arrived at its present location. For a time, scientists speculated that Sedna might be a one-off oddity produced by some unusual ancient event, perhaps a close encounter with another star when the solar system was still young and embedded in a star-forming cluster. A passing star might have perturbed Sedna's orbit into this strange configuration. But then more objects like Sedna were found. Over the following decade and a half, astronomers identified a handful of additional extreme objects with similarly detached, elongated orbits. One of these, discovered in 2014 and nicknamed the Goblin for its Halloween season discovery date, shares the same orbital family as Sedna. When astronomers plotted the orbits of all these detached objects together on a map of the solar system, the pattern was striking. Random orbits, the kind you would expect if these objects were scattered into place by random gravitational encounters, would be distributed evenly around the solar system. If you mark the direction each orbit swings out into, they should point in all different directions, spread around the sun like the spokes of a randomly constructed wheel. There should be no preferred direction. But there is a preferred direction. The extreme objects cluster together. Their orbits all swing out into space toward the same general region of the sky. They are tilted at similar angles. They share orbital characteristics that seem linked. The probability of this occurring by chance by the random coincidental alignment of objects scattered into place by unrelated events is calculated at less than 1 in 10,000. The clustering is statistically real, and it is statistically significant. The only mechanism capable of producing this kind of persistent orbital alignment is gravity. A gravitational source large enough and distant enough to influence all of these objects simultaneously to shepherd their orbits into a common orientation would need to be massive. Based on the degree of clustering and the distances involved, calculations suggest that this hypothetical body would need to be between 5 and 10 times the mass of Earth. It would be a super-Earth, or perhaps a body more like an ice giant similar to Neptune. It would orbit at a distance of several hundred astronomical units, possibly more so far from the Sun that it completes one orbit every 10,000 to 20,000 years. At that distance, such a planet would be extraordinarily difficult to detect. It would reflect very little sunlight. It would move across the sky so slowly as to be nearly stationary over years of observation. Its thermal emission, the infrared radiation it produces from its own internal heat, would be faint enough to hide against the background of more distant objects. We have extremely powerful telescopes capable of imaging very dim objects, but they must be pointed in the right direction. A planet hiding in a 2-degree patch of sky among billions of stars and galaxies might simply have not been targeted yet. Astronomers call this hypothetical planet Planet 9. It remains unconfirmed. No direct observation of the planet itself has been made. Its existence is inferred entirely from the orbital properties of the extreme trans-Neptunian objects, and there are ongoing debates in the astronomical community about whether those properties truly require a distant planet or whether other explanations, including observational biases in the surveys that found the extreme objects, might account for the clustering. But the planet hypothesis has not been disproven. It continues to drive an active search. The Vera C. Rubin Observatory, a new wide-field survey telescope under construction in Chile and scheduled to begin science operations in the mid-2020s, is expected to be a key instrument in this search. Its ability to image the entire southern sky repeatedly to great depths over its 10-year survey will either find Planet 9 if it exists or place strong constraints on where it could be hiding. Other astronomers have proposed alternative explanations for the orbital clustering. One hypothesis suggests that the combined gravitational influence of the many smaller Kuiper Belt objects themselves, not any single large planet, could produce the observed alignment. Another suggestion is that a primordial black hole, a theoretical type of microscopic black hole that might have formed in the early universe, could produce the required gravitational influence while remaining invisible to conventional telescopes. This idea is speculative, but it illustrates how seriously the anomaly is taken. The alternative to Planet 9 would need to be something equally extraordinary. Whatever the explanation turns out to be, the outer solar system has made its message clear. We do not understand this region as well as we thought we did. The Kuiper Belt has been continuously rewriting its own story. Every major instrument pointed at this region has come back with something unexpected. Arrokoth showed us that planet formation is gentle. Haumea showed us that a dwarf planet can be stretched and distorted by its own spin. Quaoar showed us that rings can exist where our physics says they should not. Eris showed us that internal geological activity can continue in worlds we had dismissed as permanently dead. The New Horizons dust counter showed us that the belt extends beyond the boundary we had drawn for it. And Sedna showed us that something massive may be waiting in the dark, controlling the orbits of the most distant worlds. Each discovery has compelled a revision to a theory that seemed, until that point, well established. The pattern is consistent. The outer solar system is more complex, more dynamic, and more surprising than our models account for. The Vera Rubin Observatory's Legacy Survey of Space and Time, a 10-year sky survey beginning in the mid-2020s, will systematically catalog millions of solar system objects, including many in the Kuiper Belt. This survey will either confirm the existence of Planet 9 or significantly narrow the parameter space where it could hide. It will also likely reveal hundreds of additional Kuiper Belt objects, potentially including objects large enough to be classified as dwarf planets. The James Webb Space Telescope will continue to study the surfaces of known Kuiper Belt objects, probing their compositions and looking for additional signs of active geology. If the cryovolcanism seen on Eris is common among large Kuiper Belt objects, Webb will find the evidence. If it is unusual, that too will be scientifically meaningful. The New Horizons spacecraft, now cruising through the region beyond the main Kuiper Belt, will continue operating through at least the late 2020s. Its instruments will keep measuring dust density, cosmic rays, and the properties of the interplanetary medium through this poorly understood region. If the second Kuiper Belt is real and substantial, New Horizons may eventually pass through it, and its dust counter will register the transition. Theoretical work is also advancing rapidly. Sophisticated gravitational simulations are testing every proposed explanation for the orbital clustering of extreme trans-Neptunian objects. Astronomers are building models that can account for the double disk structure of the Kuiper Belt, the Kuiper Cliff, and Sedna's detached orbit simultaneously. No model fits all the data yet. The anomalies pile up faster than the explanations. What the Kuiper Belt ultimately represents is something rare in modern science. A region of our own solar system that remains genuinely, profoundly not understood. We are not puzzling over fine details in an otherwise well-mapped territory. We are confronting fundamental questions about the structure, history, and boundaries of our own neighborhood. The solar system the textbooks described 8 planets, a thin asteroid belt, and then emptiness was always a simplification. Scientists knew that. But the degree to which it was a simplification and the richness of what was being omitted has been one of the most consistent surprises of the last 3 decades of planetary science. Beyond Neptune, in the cold and the dark, billions of objects are drifting in their slow orbits. Some of them preserve the original chemistry of the solar system in their frozen surfaces. Some are geologically active despite sitting at the edge of the sun's thermal influence. Some are moving in patterns that require an explanation we have not yet found. And somewhere in that darkness, according to the best reading of the available evidence, there may be a planet larger than Earth that has never been seen, photographed, or even directly suspected until very recently. We have been exploring space for decades. We have sent probes to every planet, landed on Mars, imaged black holes at the centers of galaxies, and detected gravitational waves from colliding neutron stars 50 million light-years away. And yet, within our own solar system, less than 1,000 astronomical units from home, there are fundamental questions that remain open. The outer solar system is not a postscript. It is not empty space waiting to be crossed on the way to somewhere more interesting. It is an active scientific frontier, full of objects that break rules, full of structures that demand explanation, and full of evidence pointing towards something large that we have not yet found. The search continues, and if the history of the Kuiper Belt is any guide, whatever we find out there will not look like what we expected. If the science in this video made you think differently about the solar system, consider liking and subscribing. There is a great deal more territory to cover in every direction. To fully appreciate what makes the Kuiper Belt discovery so scientifically consequential, it helps to step back and understand the broader context of how our understanding of the outer solar system has evolved over the past century, because the transformation has been dramatic and relatively recent. For most of the 20th century, the outer solar system was considered astronomically boring. After Clyde Tombaugh discovered Pluto in 1930 at the Lowell Observatory in Arizona, astronomers spent the next 6 decades assuming that Pluto was a peculiar outlier, a small, lonely world in an otherwise empty void. The idea that an entire populated belt of debris might lie beyond Neptune was proposed theoretically, but not taken seriously by the mainstream. The intellectual history begins with Gerard Kuiper himself, the Dutch-American astronomer whose name the belt carries. In 1951, Kuiper published a paper arguing that a disk of primordial material might exist beyond Pluto. His reasoning was based on solar system formation theory. If the protoplanetary disk that formed the solar system extended outward, there should be leftover material in the outer regions that never coalesced into a planet. Kuiper's specific prediction was actually somewhat different from what we now know. He thought the disk would be essentially empty in the modern era, having been scattered by Pluto's gravity, but his general intuition that something existed beyond Neptune proved correct. The idea languished for decades. Telescopes were not powerful enough to find small dark objects at those distances, and there was no strong observational evidence to motivate a dedicated search. Then, in 1992, astronomers David Jewitt and Jane Liu announced the discovery of a small object beyond Neptune. They had been conducting a systematic survey of the outer solar system for 5 years, spending telescope time that many colleagues considered wasted. The object they found, designated 1992 QB1, was small, dark, red, and sitting at about 41 astronomical units. It was the first confirmed member of what would become known as the Kuiper Belt. Jewitt and Liu's discovery opened a floodgate. Once astronomers knew what they were looking for and understood that such objects were detectable with sufficiently dedicated observing campaigns, the catalog of Kuiper Belt objects began to grow rapidly. By the late 1990s, dozens had been found. By the early 2000s, the count was in the hundreds. Today, more than 3,000 Kuiper Belt objects have been cataloged, and the estimated total population, including objects too small and faint to detect with current instruments, runs into the hundreds of billions. The 30-year gap between Kuiper's theoretical suggestion and Jewitt and Liu's discovery illustrates one of the persistent challenges of outer solar system science. The objects are too distant and too dark for casual observation. Detecting them requires large telescopes, sensitive detectors, and a willingness to spend significant observing time on a search that might yield nothing. The outer solar system rewards systematic patience in a way that more accessible parts of the cosmos do not. Understanding the orbital architecture of the Kuiper Belt also required decades of careful observation. The belt is not uniformly populated. Its objects are grouped into families that reflect how they have interacted with Neptune's gravity over billions of years. Some objects, called classical Kuiper Belt objects, orbit in stable, roughly circular paths with relatively low inclinations relative to the plane of the planets. Among these, a subset called cold classical Kuiper Belt objects, cold referring to their low orbital velocities, not. Their temperature tend to be redder and appear to have been less disturbed since their formation. Arrokoth is a member of this cold classical population, which is why it preserves such a pristine record of early solar system conditions. Other Kuiper Belt objects are grouped into what are called resonances with Neptune. A resonance occurs when an object's orbital period is in a simple whole number ratio with Neptune's orbital period. Pluto is the most famous example. It orbits the Sun twice for every 3 orbits Neptune completes, a configuration called the 2-to-3 resonance, or the 3-to-2 resonance, depending on how you frame it. This resonance relationship means that Pluto and Neptune never actually get close to each other despite orbits that seem to cross, because they are always at the right positions relative to each other when the close approach would otherwise occur. Hundreds of other objects share Pluto's resonance, and they are sometimes called Plutinos in recognition of this family resemblance. Beyond the classical belt and the resonant populations, there are the scattered disk objects, bodies with highly eccentric orbits that take them from the inner Kuiper Belt to very large distances. These objects were likely scattered outward by gravitational interactions with Neptune early in the solar system's history. Their orbits continue to evolve slowly under Neptune's influence. The scattered disk is thought to be the source of many of the short-period comets that occasionally visit the inner solar system objects, whose orbits were perturbed enough by Neptune's gravity to send them plunging inward, toward the Sun. This connection between the Kuiper Belt and the comets of the inner solar system is one of the most practically significant aspects of this region. Comets are not just icy visitors from the distant past. They are one of the mechanisms by which water and organic molecules may have been delivered to the inner solar system, including to Earth. The bombardment of the early Earth by comets and other icy bodies during the late heavy bombardment period, which occurred roughly 3.9 billion years ago, may have contributed substantially to Earth's water supply and perhaps to the chemical building blocks of life. If the Kuiper Belt is the reservoir from which these comets are drawn, and the evidence strongly supports this conclusion, then the belt has a direct causal connection to the emergence of life on Earth. The water in our oceans may have originated as frozen volatiles on objects that once drifted quietly in the outer Kuiper Belt before some gravitational nudge sent them inward. Our planet's habitability has roots in that distant cold zone. The study of cometary composition has reinforced this connection. When comets visit the inner solar system and are warmed by sunlight, they sublimate their ices, turn directly to gas, and stream away, carrying with them the chemical fingerprints of the material they are made from. Space missions have analyzed comet compositions up close. The European Space Agency's Rosetta mission spent more than 2 years orbiting Comet 67P Churyumov-Gerasimenko, delivering the Philae lander to its surface in November of 2014. The mission found a remarkably complex chemical inventory: glycine, which is an amino acid and a building block of proteins, phosphorus, a critical component of DNA and RNA, and dozens of organic molecules of varying complexity. Many of these are the same classes of molecules that chemists believe were essential precursors to the origin of life on Earth. These cometary ingredients are, in origin, Kuiper Belt ingredients. The chemistry of life's beginning may be written in the frozen surfaces of objects still orbiting quietly beyond Neptune. Pluto itself, despite losing its planetary status in 2006, deserves substantial attention in any serious discussion of the Kuiper Belt. When New Horizons flew past Pluto in July of 2015, it transmitted images that astonished the planetary science community. Pluto was expected to be a geologically dead, crater-saturated ball of ice, a world unchanged since its formation. The images showed something completely different. Pluto has a vast heart-shaped nitrogen ice plain called Tumba Regio, named in honor of its discoverer. The smooth surface of this feature tells us it is geologically young, perhaps only a few million years old. An ancient surface would be pocked with craters from billions of years of impacts. A smooth surface means the terrain has been recently renewed. Pluto, like Eris, appears to have internal processes capable of resurfacing itself. Pluto also has mountain ranges, enormous peaks of water ice rising kilometers above the nitrogen ice plains. The mountains are young by geological standards, suggesting ongoing tectonic activity. There are what appear to be ancient river valleys carved by liquid nitrogen. There is a diffuse, hazy atmosphere made primarily of nitrogen, with traces of methane and carbon monoxide extending hundreds of kilometers above the surface. At the poles, there are deposits of different ices that migrate seasonally as Pluto's extreme orbit carries it closer to and further from the Sun. Everything about Pluto's geology suggests a world that is dynamic, active, and far more complex than a cold, dead rock should be. The source of this internal activity is not fully resolved, but radioactive decay in the rocky core, augmented possibly by the release of heat from ancient impacts, is the leading hypothesis. Charon, Pluto's largest moon itself, roughly half the diameter of Pluto, making the two bodies effectively a binary dwarf planet system, also showed surprises. Images from New Horizons revealed a deep canyon system stretching across Charon's surface, evidence of ancient tectonic activity when Charon may have had a subsurface ocean that subsequently froze and expanded, cracking the crust from within. Charon's north pole is covered in a dark reddish material that appears to be organic compounds. Tholins, formed when methane escaping from Pluto's atmosphere is captured by Charon's weak gravity, and then chemically altered by ultraviolet radiation and cosmic rays. The Pluto system is, in miniature, a remarkably complex world. The fact that it sits in the Kuiper Belt and shares the region with thousands of other objects raises immediate questions. How many of those other objects are equally complex? How many have subsurface oceans, ongoing geological activity, and chemically interesting surfaces? The answer, based on what we are finding with Webb and other instruments, appears to be more than we expected. The discovery of active geology on small, cold worlds is reshaping how planetary scientists think about the population of potentially habitable environments in our galaxy. The classic definition of a habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, is increasingly seen as an incomplete framework. Worlds far outside the traditional habitable zone, where the sun's warmth is irrelevant, can maintain liquid water in their interiors through internal heat generated by tidal forces, radioactive decay, or residual heat from formation. The icy moons of Jupiter and Saturn, Europa, Ganymede, Callisto, Enceladus, Titan are the most prominent examples, but the Kuiper Belt dwarf planets are expanding this picture further into the outer solar system. The concept of the extended habitable zone, or the internal habitable zone, is now an active area of astrobiological research. If life can arise in environments driven by internal heat rather than stellar radiation, then the number of potentially habitable worlds in the galaxy increases enormously. Rocky and icy bodies of sufficient mass, even those orbiting far from their stars, or even those that have been ejected from their systems and drift freely through interstellar space, might harbor liquid water in their interiors. The Kuiper Belt objects are, in this context, the closest examples of a category of worlds that may be abundant throughout the galaxy. Returning to the orbital anomalies of the extreme outer solar system, the case for Planet 9 has been both strengthened and complicated by subsequent analysis. The initial statistical argument, made in 2016 by astronomers Konstantin Batygin and Mike Brown, was based on the clustering of 6 extreme trans-Neptunian objects. Their calculations suggested that the probability of this clustering arising by chance was about 0.007%. The paper generated immediate and widespread scientific interest. Subsequent work has refined and complicated the picture. Some analyses have suggested that observational bias, the fact that surveys of the outer solar system tend to look in certain regions of the sky more than others, could artificially create the appearance of clustering, even if the underlying distribution is random. If surveys consistently observe more sky in certain directions, the objects they find will be more concentrated there, creating a clustering signal that does not reflect an underlying physical cause. Other analyses have maintained that even after correcting for observational bias, the clustering signal remains statistically significant. The debate involves detailed modeling of survey coverage, detection efficiency, and the expected distribution of extreme trans-Neptunian objects under different orbital architectures. It is an ongoing and genuinely unresolved scientific controversy. Batygin and Brown have continued to refine their Planet 9 hypothesis. Their most recent models suggest that the planet, if it exists, would need to be somewhat smaller than their original estimate, perhaps 3 to 5 times Earth's mass, rather than 5 to 10, and located at a distance of approximately 400 to 500 astronomical units. At that distance and mass, it would have an apparent brightness roughly 100 times fainter than the faintest object yet detected by large sky surveys. Finding it will require either a very lucky targeted observation pointing a large telescope at exactly the right patch of sky, or the completion of the Rubin Observatory's systematic survey, which should be sensitive enough to detect it if it is there. The alternative to Planet 9 is itself scientifically interesting. If the clustering of extreme trans-Neptunian objects turns out to be a statistical artifact, if careful survey modeling shows it is consistent with a random distribution, then we avoid one puzzle at the cost of another. The detached orbit of Sedna, which requires an explanation regardless of whether the clustering is real, becomes an even more isolated anomaly. Sedna's orbit cannot be explained by any known process, even if Planet 9 does not exist. Some other explanation must be found. Proposals include a star that passed close to the early solar system when it was still embedded in its birth cluster, gravitationally tugging Sedna's orbit into its current configuration before moving on. This scenario is plausible. The Sun almost certainly formed in a dense star-forming cluster where such encounters were relatively common, and the cluster would have dispersed within the first 100 million years of the solar system's history. A stellar flyby could have perturbed the outer reaches of the young solar system and left behind a population of oddly orbiting objects that we are only now discovering. In this scenario, the legacy of the Sun's birth environment is still visible, encoded in the orbits of Sedna and its family. Another proposal involves the capture of objects from another planetary system. During the dispersal of the birth cluster, The Sun may have captured material from neighboring stars whose planetary systems were being disrupted by close encounters. Some of the most extreme objects in the outer solar system might not be native. They might be interstellar immigrants, captured into solar orbits billions of years ago. This would explain their unusual orbits without requiring any currently undetected planet. The proposal gained some additional context from the 2017 detection of the first confirmed interstellar visitor to our solar system, an object designated Oumuamua. This cigar-shaped body entered the solar system from interstellar space, passed through the inner system at high speed, and accelerated out again in a way that puzzled astronomers, because it appeared to have a non-gravitational force acting on it, possibly outgassing from a comet-like composition, possibly something more exotic. A second interstellar object, Comet Borisov, was detected in 2019 and showed a clearer comet-like nature. These confirmed interlopers from other stellar systems demonstrated that interstellar material does pass through our solar system, lending credibility to the idea that some captured objects might have entered in the early solar system when such captures were geometrically more probable. The question of where the outer boundary of the solar system truly lies is itself scientifically unresolved and depends on how you define the boundary. If you define it gravitationally, the region where the Sun's gravity dominates over the gravity of other stars and the galactic tide, then the solar system extends to roughly 200,000 astronomical units, well into the outer Oort cloud. If you define it by the presence of objects bound to the Sun, the boundary is wherever the outermost Oort cloud comets orbit, which is similar. The newly discovered outer population of Kuiper Belt objects at 70 to 90 astronomical units is simply the next layer in an onion whose full extent we have not yet mapped. Between 50 astronomical units and perhaps 50,000 astronomical units, there is likely a continuous gradient of objects, some more concentrated in the scattered disk, some in the inner Oort cloud, some in the outer Oort cloud. We have sampled portions of this population, but nothing like a complete census. The Rubin Observatory's survey will extend our census out to several hundred astronomical units for the largest objects. Beyond that, detection becomes dependent on dedicated large aperture targeted searches or future space-based wide-field infrared telescopes that do not yet exist. The complete map of the outer solar system is a project measured in decades and generations of astronomers. What has changed is our sense of what we will find when we look. A generation ago, the outer solar system was assumed to be simple and empty, a quiet periphery surrounding the interesting inner system. Everything we have found suggests the opposite. The outer solar system is complex, varied, active, and still capable of hiding major discoveries. The transition from assumed emptiness to known complexity has been one of the more dramatic reversals in modern planetary science, and it is not yet complete. The infrastructure for continued discovery is being built. The Rubin Observatory will survey the sky to unprecedented depth, expected to catalog roughly 10 million solar system objects over its 10-year primary mission, including tens of thousands of new Kuiper Belt objects and potentially the first direct detection of Planet 9. The Roman Space Telescope, NASA's next flagship space telescope, scheduled for the late 2020s, will add infrared capabilities that complement Rubin's optical survey. James Webb continues to study the compositions of known outer solar system bodies in detail. And if funding and technology cooperate, a dedicated outer solar system mission, possibly an interstellar probe concept that has been under discussion at NASA, could send a spacecraft into the outer Kuiper Belt and beyond over the course of several decades. The science emerging from the Kuiper Belt has also informed how astronomers interpret observations of other planetary systems. We can now image debris disks around other stars with enough resolution to see their structures' rings, gaps, and outer extensions. When we see a double ring structure around another star, we can hypothesize that it reflects the same kind of architecture as our own system, an inner Kuiper Belt, a gap cleared by a planet we cannot directly see, and an outer extension that marks the full reach of the disk. The Kuiper Belt gives us a ground truth example, a system we can study up close that allows us to interpret the disk structures around other stars with more confidence. This comparative planetology is becoming one of the most productive methodologies in modern astronomy. By combining detailed study of our own solar system's components with the statistical sample of thousands of exoplanetary systems and their associated disk structures, Astronomers can build much more robust theories of planetary system formation and evolution than either approach could achieve alone. The Kuiper Belt is not just a local curiosity, it is a calibration point for a much larger scientific program aimed at understanding how planetary systems form across the galaxy. The broader question lurking beneath all of this research is whether our solar system is typical. For a long time, planetary scientists assumed that our system, a star surrounded by a few rocky inner planets and several giant outer planets, with a belt of rocky debris and then a belt of icy debris and then the Oort cloud, represented a common template for planetary system architecture. The explosion of exoplanet discoveries over the past 2 decades has revealed that planetary systems are far more diverse than anyone expected. Systems with hot Jupiters sitting close to their stars, systems with multiple super-Earths packed into orbits closer than Mercury's, systems with no giant planets at all, systems where the planets are arranged in intricate resonance chains. Our solar system, by some measures, now appears to be unusual. The absence of super-Earths in the inner system, a category of planet found in the majority of other stars' planetary systems, is a notable feature. The specific arrangement of our giant planets, particularly the relationship between Jupiter and Saturn, may have played a decisive role in stabilizing the inner solar system and preventing the growth of super-Earths there. Some models of solar system formation suggest that without Jupiter acting as a gravitational barrier, the inner planets might have grown much larger or accumulated much more volatile material. In this context, the Kuiper Belt structure, and in particular, the hypothetical Planet 9, takes on additional significance. If Planet 9 exists, it would mean that our solar system does have a super-Earth, just not where we have been looking. It would mean that the category of planet most commonly found in other stellar systems is also present in our own, hidden in the dark at distances we have not yet adequately surveyed. The discovery of Planet 9 would simultaneously resolve the anomalies of the outer solar system and reconcile our planetary system with the common pattern seen elsewhere in the galaxy. It would also raise the question of how Planet 9 got there. Current theories of planet formation do not easily produce a planet at several hundred astronomical units. One possibility is that Planet 9 formed in the inner solar system alongside the other giant planets, but was gravitationally ejected into a distant orbit by a close encounter with Jupiter or Saturn early in the solar system's history. Another possibility is that Planet 9 is a captured rogue planet, a world that formed around another star, was ejected from that system, and was then gravitationally captured by our Sun during the early clustering period when many stars were in close proximity. A captured rogue planet would explain Planet 9's unusual orbit without requiring it to have formed in place. These are not scenarios that can currently be distinguished observationally. If Planet 9 is found, determining its origin will require understanding its composition, its atmospheric properties, and the details of its orbit in ways that will take years of follow-up study. The discovery would answer one question while opening several others. This is the nature of science at the frontier. Each answer comes with a set of new questions attached. The history of Kuiper Belt research is a demonstration of how quickly a new observational capability can overturn an old assumption, and how much there remains to discover, even in the regions of space we believed we knew well. At the turn of the 21st century, the Kuiper Belt had only just been discovered and contained fewer than 100 known objects. Now, there are thousands. Then, the outer solar system was assumed to extend to 50 astronomical units and then be effectively empty. Now there are 2 populations of Kuiper Belt objects separated by a gap, and the outer one was found just in the last year or 2. Then, Pluto and the Kuiper Belt were thought to be cold, dead, geologically inert relics. Now we know that active geology, fresh methane, and recently resurfaced terrain are features of these worlds. Then, the orbital anomalies of a handful of extreme objects were considered statistical noise. Now, they are the primary evidence for an undiscovered planet. The pace of discovery in this region has been consistently faster than anticipated, and there is no reason to think it will slow. The instruments are getting more powerful. The survey programs are getting more systematic. The theoretical models are getting more sophisticated. Every year, the Kuiper Belt yields something that had not been predicted. The solar system beyond Neptune is not the end of something. It is the beginning of a scientific program that will occupy astronomers for the rest of this century. It is a region where fundamental questions about how planets form, about the extent of our solar system, about the architecture of planetary systems across the galaxy, and perhaps even about the conditions that made life on Earth possible, are waiting for answers. Those answers will not come quickly or easily. They will require patience, repeated observation, sophisticated analysis, and perhaps a few more spacecraft heading outward into the dark. But the last 3 decades have made it clear that the effort is worthwhile, that beyond the familiar boundary of the planetary system, in the cold and the dim, there is more waiting to be understood than we had imagined. We are still mapping our own backyard, and the map keeps getting larger. One of the most intriguing aspects of Kuiper Belt research that is rarely discussed in popular accounts is what these objects can tell us about the Sun's own history. Stars, including our Sun, do not form in isolation. They form in dense molecular clouds where thousands of stars condense simultaneously from collapsing regions of gas and dust. For the first several tens of millions of years, these newborn stars are packed together in stellar nursery star clusters, where gravitational encounters between neighboring stellar systems are common. Our Sun was born in one of these clusters, approximately 4.5 billion years ago. We know this because several isotopic signatures preserved in ancient meteorites, rocky fragments that have fallen to Earth from the early solar system, record the brief presence of short-lived radioactive elements that can only be produced in the final stages of a massive star's life and distributed in a stellar explosion called a supernova. The meteoritic evidence suggests that a supernova occurred very close to the young solar system, seeding it with freshly produced radioactive material that was then incorporated into the earliest solid objects to condense. This supernova was not a random coincidence. It happened because the solar system was embedded in a dense stellar cluster where massive stars, which live short, violent lives and explode as supernovae, were forming alongside our Sun. The Sun was part of a busy neighborhood for its first 100 million years or so, before the cluster gradually dispersed as the molecular cloud's gas was blown away by stellar winds and radiation. During this period of cluster membership, the outer regions of the young solar system would have experienced significant perturbations. Close stellar encounters could have tugged on material in the outer solar system, reshaping orbits and perhaps populating the detached disk, the region where Sedna and its family orbit through gravitational nudges that no longer occur today. The Oort cloud itself may have been assembled largely during this period, when passing cluster members could stir material to very large distances from the Sun. After the cluster dispersed, the Sun entered the galactic field. The general stellar population of the Milky Way and the frequency of close stellar encounters dropped to its current very low level. A truly close stellar encounter, a star passing within a light year of the Sun, is expected to happen only once every several hundred million years, on average. And even those distant encounters have only mild effects on the outer solar system. The intense sculpting phase ended when the cluster dispersed. What this means is that the current outer solar system is, in a sense, the frozen record of a much more dynamic early period. The strange orbits of Sedna and the Goblin and the other extreme trans-Neptunian objects are fossils of gravitational interactions that happened billions of years ago and cannot happen today. They are ancient signatures that still persist because there is nothing in the current solar system energetic enough to erase them. Reading these fossil orbits is one of the most challenging problems in observational and theoretical astronomy. To decode them, scientists need to work backward. Given the current configuration of orbits, what initial conditions and what history of gravitational encounters would produce this result? The mathematical problem is the reverse of a normal calculation, and there are many different possible histories that could lead to similar present configurations. Planet 9 is one candidate history shaper. Cluster encounters are another. A combination of both is a third. Distinguishing between these possibilities requires more data, more extreme trans-Neptunian objects with well-measured orbits, so that the statistical properties of the population can be determined with greater precision. A few dozen currently known objects are not enough to reliably separate the Planet 9 signal from the noise of observational bias and the background scatter. Several hundred well-measured extreme objects would be transformative. The Rubin Observatory is expected to provide them. The Kuiper Belt's role in delivering material to the inner solar system also extends to a phenomenon called the late heavy bombardment, which left a permanent mark on every solid body in the inner solar system. Between approximately 4 billion years and 3.8 billion years ago, the rate of impacts on the Moon, Mars, and presumably Earth spiked dramatically compared to both earlier and later periods. The lunar highlands, the ancient, heavily cratered terrain visible on the Moon's near side, are largely the product of this bombardment. The cause of the late heavy bombardment is debated. One influential model, called the Nice model after the city in France where it was developed, proposes that the giant planets were not always in their current orbits. Instead, they are proposed to have undergone a period of orbital instability roughly 600 million years into the solar system's history. Jupiter and Saturn, in this model, entered a gravitational resonance with each other that destabilized the outer solar system. Uranus and Neptune migrated outward rapidly, plunging through the primordial Kuiper Belt and scattering its objects in all directions, some outward into the Oort cloud, some inward into the inner solar system, where they became the impactors of the late heavy bombardment. In the Nice model, the Kuiper Belt's current population is the remnant of a much larger primordial belt. The migration of Neptune depleted the belt by roughly 90 to 99%, ejecting most of its mass into the Oort cloud or out of the solar system entirely. The belt we observe today, massive as it is, may be a pale shadow of its original scale. The implications of this model are significant for understanding Earth's early history. If the Nice model is correct, then the late heavy bombardment delivered an enormous influx of impactors to Earth at a time when life was either just beginning or about to begin. Geochemical evidence suggests that life existed on Earth by at least 3.7 billion years ago, and possibly earlier, meaning that life either arose in the bombardment period, survived through it, or arose very quickly after it ended. The bombardment would also have delivered substantial quantities of water and organic molecules from the icy Kuiper Belt impactors, potentially contributing to the conditions that made life possible. Not all scientists accept the Nice model or its specific timeline. Alternative models of giant planet migration produce different bombardment histories, and the lunar record of the late heavy bombardment has been reinterpreted by some researchers as less extreme than previously believed. The debate about what exactly happened to the outer solar system early in its history and how that history shaped the conditions on Earth is an active one. But the Kuiper Belt sits at the center of it, as both the reservoir of the impactors and the witness to the migration of Neptune. The connection between the Kuiper Belt and Earth's habitability is thus bidirectional. The belt received its structure from the planetary migrations that also delivered water and organics to the inner solar system. It continues to supply short-period comets to the inner system, which occasionally impact Earth and add fresh volatiles. And its geologically active dwarf planets demonstrate that the volatile-rich objects of the outer solar system are chemically complex in ways that could be significant for understanding the chemistry of life's origin. Turning to the specific compositional details that Webb and other telescopes have revealed, the variety of surface compositions across Kuiper Belt objects is far richer than early estimates suggested. Methane ice, nitrogen ice, water ice, ammonia, carbon monoxide, carbon dioxide, and complex organic compounds called tholins have all been detected on various outer solar system bodies. The relative proportions of these materials vary significantly from object to object, creating a palette of surfaces ranging from bright white dominated by fresh nitrogen or methane ice to dark red dominated by tholins and other processed organics. Tholins are particularly interesting from an astrobiological perspective. They are produced when simple molecules like methane and nitrogen are exposed to ultraviolet radiation or energetic particles and undergo chemical reactions that build more complex molecular structures. The reddish color of many Kuiper Belt objects is largely due to the accumulation of these tholins on their surfaces over billions of years. In laboratory experiments, tholins have been produced that contain amino acid precursors, molecules that, under the right conditions, can assemble into amino acids, the building blocks of proteins. Titan, Saturn's large moon, is covered in tholins and has served as the best-studied example of this chemistry in the solar system. The chemistry on Titan's surface and in its thick atmosphere provides a window into the kinds of prebiotic chemistry that might occur on other tholin-rich bodies. Kuiper Belt objects, whose surfaces are coated in this same class of material, are therefore potentially significant as natural laboratories for understanding the chemistry that preceded life. The challenge is studying this chemistry in detail at Kuiper Belt distances. A spacecraft mission to a major Kuiper Belt object. one designed specifically to analyze surface and subsurface composition, measure internal heat, and study geological activity, would return extraordinary data. The New Horizons mission to Pluto and Arrokoth demonstrated both the scientific value and the technical feasibility of such missions. A next-generation mission with more capable instruments and perhaps a surface lander is an aspiration that several teams in the planetary science community are actively advocating for. NASA's Decadal Survey, the prioritization process that guides planetary science mission selection over a 10-year period, identified outer solar system exploration as a high priority. Whether a dedicated Kuiper Belt mission will be funded depends on the competitive landscape of planetary science priorities and the available budget. The timeline of Kuiper Belt exploration, looked at in its totality, is a story of accelerating discovery, driven by improving technology. The region was unknown before 1992. By 2005, enough of its architecture was understood that the discovery of Eris forced a redefinition of the term planet. By 2015, New Horizons had revealed a geologically complex Pluto with mountain ranges, young terrains, and an active atmosphere. By 2019, Arrokoth had shown us the gentleness of planet formation. By 2023, Quaoar's impossible ring had been catalogued. By 2024 and 25, a second Kuiper Belt had been tentatively mapped. And in the background throughout this period, the case for Planet 9 has been built, debated, refined, and left unresolved. Each 5-year interval has brought discoveries that change the questions being asked. There is no reason to expect this pace of discovery to slow. The instruments coming online in the next decade are more capable than anything that has operated previously. The theoretical frameworks are more sophisticated. The community of researchers studying the outer solar system has grown substantially. What will the outer solar system look like to planetary scientists in 2035? Almost certainly, the Rubin Observatory's survey will have either found Planet 9 or placed it in a much smaller region of parameter space. The catalog of Kuiper Belt objects will be several times larger. Webb will have accumulated detailed compositional data on dozens of dwarf planets and Kuiper Belt objects. New Horizons will either still be operating and sending back data from deep beyond the Kuiper Belt, or its mission will have concluded after more than 30 years of operation since its launch in 2006. A new outer solar system mission may be in development or already launched. And almost certainly, there will be discoveries that nobody is predicting today, observations that do not fit current models, objects that behave in unexpected ways, structures that require new theoretical frameworks. This has been the consistent pattern. The outer solar system delivers surprises faster than predictions can be made. The scientific significance of the Kuiper Belt ultimately rests on its role as a preservative. The outer solar system is cold, dark, and quiet. The objects there have experienced so little processing since their formation that they retain the chemical and physical signatures of the solar system's beginning. Every measurement made of a Kuiper Belt object's composition, structure, or geological history is a measurement of the solar system's formation. Every anomalous orbit is a fossil of an early gravitational event that no longer occurs. Every active world is evidence that internal heat persists in places we assumed were dead. This region is not a periphery, it is an archive. And like any archive, its value lies in the information it contains, information about origins that cannot be recovered from any other source, because the processes that produced it operated billions of years ago and will never be repeated. The scientists who study the Kuiper Belt are, in a very direct sense, archaeologists of the solar system. They sift through ancient frozen debris in search of records of a past too remote and too chaotic for any other scientific discipline to access. The records are there, encoded in orbital mechanics and surface chemistry and geological history, waiting to be decoded. The tools to decode them are improving steadily. The scientific community motivated to use those tools is growing. The questions being asked are sharper and more specific than they were a decade ago. The Kuiper Belt has moved from being a theoretical curiosity to a central topic in planetary science, and it shows no sign of giving up its secrets easily. That resistance to easy answers is, paradoxically, what makes it so scientifically valuable. The regions of the universe that yield simple, confirmatory results do not drive science forward. It is the anomalies, The ring that should not be there. The world that should be dead but is not. The orbit that no known force can explain that force. The field to reckon with the limits of its current understanding. The Kuiper Belt is currently generating more anomalies per square astronomical unit than any other region of the solar system. This is not a problem to be frustrated by. It is an invitation. The outer solar system is inviting astronomers to look more carefully, think more creatively, and build better models. It is offering a scientific program that will take generations to complete. And in the process of that program, it may answer questions that range from the formation of our solar system to the distribution of life in the galaxy. We have been looking at the night sky for thousands of years. We have studied the planets since before there was a word for science. And we are still finding major structures and fundamental mysteries in our own solar system within distances that a spacecraft can reach in a human lifetime. The universe is not finished revealing itself. And the Kuiper Belt, sitting in the relative dark just beyond the familiar borders of home, is one of the best places to watch what it does next. There is another dimension to the Kuiper Belt story that is easy to overlook amid all the talk of distant objects and orbital mechanics. The human dimension of how this region came to be understood. Scientific knowledge does not arrive fully formed. It is built through the accumulation of observations, the construction of theoretical frameworks, the competition between alternative explanations, and the slow process by which a community of researchers reaches consensus on what the evidence means. The history of Kuiper Belt science is a case study in how modern planetary science actually works. When David Jewett and Jane Liu began their survey in the 1980s, they were not following an approved NASA program or working from a well-funded large project. They were persistent individual scientists who chose to devote their limited telescope time to a search that most of their colleagues considered unpromising. Jewett has described the experience of spending years pointing a telescope at empty-looking regions of sky, night after night, without finding anything. The patience required to conduct this kind of systematic search and the conviction that the search was worthwhile despite the absence of immediate results is a quality that does not receive enough credit in popular accounts of scientific discovery. The same quality characterized the search for the extreme trans-Neptunian objects. After Sedna's discovery in 2003, the number of known detached objects grew very slowly. The surveys required were large in scale, painstaking in execution, and yielded only a handful of relevant objects over more than a decade. The statistical analysis that Batygin and Brown performed in 2016, the paper that introduced the Planet 9 hypothesis, was possible because those objects had accumulated slowly over years of dedicated searching. The science of the Kuiper Belt is also a story of international collaboration. The telescopes used for Kuiper Belt surveys span several continents and several nations. The Subaru telescope that found the outer population is operated by Japan's National Astronomical Observatory. The Dark Energy Survey, which contributed several important trans-Neptunian object discoveries, used a telescope in Chile operated by a consortium of American and international institutions. The James Webb Space Telescope is a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. The upcoming Rubin Observatory is primarily American in funding, but international in its scientific community. The New Horizons mission itself required years of advocacy, multiple redesigns, and competition against other mission proposals before receiving approval. After launch, it spent more than 9 years in cruise before its encounter with Pluto, a period during which the science team maintained the mission's scientific program, kept the instruments healthy, and found the Arrokoth target for an extended mission that had not been planned when the spacecraft launched. The successful encounter with Arrokoth required a maneuver executed at a distance of more than 6 billion kilometers, with a communication delay of over 6 hours each way, and on hardware that had already been operating continuously for more than 13 years. These are not incidental details. They illustrate the scale of commitment, patience, and international cooperation required to do outer solar system science. The Kuiper Belt has rewarded that commitment generously, with discoveries that have changed our understanding of how the solar system formed and what lies at its edges. But the commitment had to come first, sustained over decades before the most important results appeared. The discovery of the second Kuiper Belt, the outer population at 70 to 90 astronomical units, also has a human story. The Subaru telescope's wide-field camera, called the Hyper-Suprime Cam, was an instrument developed over many years specifically to enable wide-field imaging surveys of unprecedented depth. Pointing this instrument at the right regions of sky to find faint, distant objects requires not just the technological capability, but also the allocation of telescope time, which is competed for through a peer review process. The team that found the outer population had to argue successfully that their search was a high-priority use of one of the most sought-after telescopes in the world. When their results were announced in late 2024 and into 2025, the initial response from the community was a combination of excitement and healthy skepticism. The outer population is still not definitively characterized. The number of confirmed members remains small enough that alternative explanations, including the possibility that the clustering is real but not as densely populated as first suggested, have not been ruled out. Follow-up observations are ongoing. This is how science works at the frontier. Discoveries are announced, scrutinized, partially confirmed, debated, and eventually either incorporated into the standard model or qualified and revised. The outer Kuiper Belt is currently at an early stage in this process. Within a few years, the Rubin Observatory's systematic survey will either confirm the outer population unambiguously with many more detected objects, or the picture will change. The sociology of how these results propagate through the scientific community is also worth considering. Major planetary science results are typically announced through peer-reviewed journals and then presented at conferences, particularly the Lunar and Planetary Science Conference held annually in Texas, and the Division for Planetary Sciences meeting held each fall. Preprints are posted simultaneously to the Arxiv server, a public repository where scientific papers are shared before formal peer review. Within hours of a significant outer solar system paper appearing on Arxiv, it is being read and discussed by researchers around the world. Social media has accelerated this process in ways that have both benefits and drawbacks. Exciting results spread quickly, reaching large audiences before they have been fully vetted. The Planet 9 hypothesis is a good example. It generated enormous public interest immediately upon publication, before the scientific community had time to assess its statistical foundations carefully. The subsequent years of debate about observational bias and the robustness of the clustering signal have been less widely reported than the initial announcement. Public understanding of the Planet 9 situation today is probably less nuanced than the current scientific understanding warrants. This gap between public perception and scientific nuance is a persistent challenge for any field at the frontier of knowledge. The Kuiper Belt, with its dramatic storylines, a hidden planet, geologically alive worlds, rings that defy physics, is particularly vulnerable to oversimplification. The reality, as is usually the case in science, is more complicated than the headlines suggest, but also more interesting when understood in its full complexity. The compositional diversity of Kuiper Belt objects is one area where the full picture is significantly more nuanced than popular accounts convey. Spectroscopic surveys have revealed that Kuiper Belt objects fall into distinct color classes. Some are very blue-gray, others are reddish, and others are extremely red, sometimes called ultra-red matter. The color distribution is not random. It correlates with orbital properties in ways that tell us something about the history of the objects. Cold, classical Kuiper Belt objects, the ones with low orbital inclinations and circular orbits, like Arrokoth, tend to be among the reddest objects in the solar system. Their red color comes from the accumulation of tholins on surfaces that have been exposed to cosmic radiation for billions of years without significant resurfacing. The cold classical population appears to have formed in place in the outer Kuiper Belt and has never been strongly disturbed. Its red surfaces are a record of undisturbed exposure to the space environment over the full age of the solar system. Hot classical Kuiper Belt objects, a misleading name, since hot refers to their orbital energy rather than their temperature, tend to be less red. They appear to have been scattered from their original formation locations into their current orbits during the early dynamical evolution of the solar system, and this scattering may have mixed different compositional types and refreshed some surfaces. Their slightly less extreme colors may reflect different formation locations, different irradiation histories, or differences in surface composition. The scattered disk objects and the resonant populations show yet another color distribution, generally intermediate between the cold classical and dynamically excited populations. Mapping these color distributions and understanding what they tell us about the formation and evolutionary history of the outer solar system is an active area of research that benefits from every new compositional measurement. Webb's ability to study surface compositions in detail, including distinguishing the isotopic signatures of different ices, as it did for the fresh methane on Eris, will be transformative for understanding what these color differences mean chemically. The instrument is sensitive enough to detect molecular species that ground-based telescopes miss and to measure isotopic ratios that carry information about the temperature and pressure conditions under which the ice formed. Beyond compositional diversity, the size distribution of Kuiper Belt objects carries information about the population's collisional history. In a population of small bodies that collide with each other over billions of years, collisions gradually grind large objects down into smaller ones. The resulting size distribution, the relative abundance of objects of different sizes, reflects both the original distribution at formation and the subsequent collisional grinding. Measuring the Kuiper Belt size distribution across a wide range of sizes requires detecting the faintest and smallest objects, which is technically challenging. Current measurements suggest that the Kuiper Belt size distribution is not a simple power law. There are features breaks in the distribution at particular sizes that suggest the population has been shaped by a combination of primordial accretion processes and subsequent collisional evolution. Understanding these features quantitatively requires larger and more complete object catalogs, which the Rubin Observatory will provide. The binary fraction of Kuiper Belt objects, the fraction that exists as gravitationally bound pairs, is another diagnostically important measurement. Among cold classical Kuiper Belt objects, the binary fraction is remarkably high, estimated at roughly 30% or more. This means nearly a third of the cold classical objects are actually pairs of roughly equal-sized bodies orbiting each other, rather than single objects. Arrokoth, whose contact binary nature we discussed, is the endpoint of a bound binary system that eventually merged. Most cold classical binaries have not yet merged. They continue as separated pairs. The high binary fraction in the cold classical population and the specific properties of these binaries' wide separations, roughly equal masses, are constraints on the formation mechanism. They are very difficult to explain if the cold classical objects form through high-speed collisional accretion, because violent collisions tend to disrupt pairs rather than create them. They are naturally explained by the streaming instability model of formation, in which clumps of pebbles collapse gravitationally into bound binary systems as a natural outcome of the process. The high binary fraction of cold classical Kuiper Belt objects is therefore independent confirmation of the same formation model that Arrokoth's gentle contact binary morphology supports. Each line of evidence converges. The color distributions, the binary fractions, the contact binary morphologies, the size distributions, they all point toward a coherent picture of the cold classical Kuiper Belt as a pristine, relatively undisturbed population that formed gently in place from the streaming instability process. This picture is now well established enough to be considered a scientific consensus, though details continue to be refined. The hot classical population, scattered disk, and resonant populations tell a different story, one of dynamical evolution, scattering, and mixing during the giant planet migration period. These populations are less pristine, more diverse, and harder to interpret cleanly. Their study requires disentangling the signatures of original formation from the signatures of subsequent dynamical processing, which is challenging when the processing was violent enough to scramble the original conditions. What emerges from all of this research is a picture of the outer solar system as a layered record of the solar system's history. The innermost layers, the hot populations, and scattered disk objects record the chaotic period of giant planet migration and collisional evolution. The cold classical belt sits atop this as an undisturbed stratum, preserving the primordial conditions of formation. And, beyond the classical belt, in the detached disk and the extreme trans-Neptunian objects, lies a record of even earlier events, stellar encounters, the birth cluster, and perhaps the gravitational influence of a world we have not yet found. Reading this record is the fundamental task of outer solar system science. It is not a simple task, and it will not be completed quickly. But the last 3 decades have demonstrated that the record is there, that it is accessible with sufficient technological effort, and that it contains more information than early researchers suspected. The Kuiper Belt began as a theoretical idea. It became a real population when the first member was detected. It became a scientific frontier when Pluto and its neighbors revealed unexpected complexity. And it has now become one of the most scientifically rich and consequential regions in the solar system, connecting the formation of planets to the origin of life and connecting our local neighborhood to the broader context of planetary systems across the galaxy. The story is not finished. The most interesting chapters may be ahead of us: the confirmation or refutation of Planet 9, the characterization of the outer belt, the detailed geological study of active dwarf planets, and discoveries that have not yet been imagined. But enough of the story has been told to recognize its outlines. The outer solar system is vast, complex, ancient, and still capable of surprise, and we are only beginning to read it. If questions like these sit at the edge of what you find worth thinking about, subscribe and keep watching. The outer solar system will give us more material for years to come. To fully close the loop on where Kuiper Belt science stands today, it is worth pausing on one of the most philosophically striking aspects of this field: the sheer improbability of knowing what we know. Consider what it takes to detect an object like Sedna. Sedna is a world roughly half the diameter of Pluto, already a small world by any standard. It sits at a minimum distance of 76 astronomical units and spends most of its 11,400-year orbit much farther away than that. At its detection distance, the light hitting its surface from the Sun, already diminished to roughly 1/1600th of the intensity that reaches Earth, must bounce off its dark reddish surface, travel back across billions of kilometers of space, enter a telescope mirror, pass through a camera system, and land on a detector sensitive enough to register the difference between it and the background sky. The entire signal is a handful of photons per second. Yet, we found it. And not only did we find it, we measured its orbit precisely enough to determine that it does not fit the known gravitational framework of the solar system. The precision of the measurement was sufficient to identify a new scientific problem. That is a remarkable statement about the state of modern observational astronomy. The detection of the outer Kuiper Belt population at 70 to 90 astronomical units represents a similar achievement. Objects at that distance, if they are small, say, a few hundred kilometers in diameter, reflect so little light that detecting them requires staring at the same patch of sky for extended periods and then applying sophisticated image subtraction techniques to pull faint moving objects out of the background of stationary stars and galaxies. The Subaru Hypersuprime Cam can image an enormous field of view, but the objects it finds at these distances are so faint that confirming their distance requires follow-up observations and careful orbital analysis. The precision with which the New Horizons dust counter detected elevated dust density beyond the Kuiper Cliff is another example. The instrument is a simple device, a stack of films sensitive to impacts from tiny dust particles, but interpreting its readings requires careful modeling of every possible source of background signal, including impacts from interstellar dust that is not related to the solar system at all. The conclusion that there is more dust in the outer region than expected was not simple to draw. It required years of data collection and careful analysis. The methods by which planetary scientists work are, in many cases, as interesting as the results they produce. Transit surveys, occultations, astrometry, spectroscopy, thermal emission measurements. Radar ranging the toolkit of outer solar system science is diverse and constantly expanding. Some of the most powerful techniques are relatively recent. The use of stellar occultations, watching what happens when a Kuiper Belt object passes in front of a background star, allows precise size measurements, atmospheric detections, and ring discoveries for objects too faint and too small to image directly. Quaoar's ring was discovered through a stellar occultation campaign. Pluto's atmosphere was first measured this way decades before New Horizons arrived. Occultation campaigns require coordinating multiple telescopes spread across a wide geographic area because the shadow of a small Kuiper Belt object crossing a background star is only a few hundred kilometers wide. You need to be in the right place on Earth when the shadow passes. Predicting exactly when and where this will happen requires knowing the object's orbit and the background star's position to very high precision, a problem that the Gaia Space Telescope, a European astrometry mission, launched in 2013, has dramatically improved by providing extraordinarily precise positions for more than 1 billion stars. Gaia's catalog has enabled a new generation of occultation campaigns by making it possible to predict stellar occultations with the precision needed to position portable telescopes in the shadow path. Several rings and irregular shapes of Kuiper Belt objects were discovered using occultations enabled by Gaia astrometry. This is an example of how technology in one area, stellar astrometry, enables discovery in a completely different area, Kuiper Belt science. Scientific progress rarely comes from a single instrument or a single technique. It comes from the combination of multiple approaches, each providing a different piece of the picture, and the synthesis of these pieces into a coherent understanding. The Kuiper Belt story is built from occultations, direct imaging, spacecraft flybys, dust counters, spectroscopy, gravitational modeling, and population statistics. No single method could have produced the current understanding on its own. Looking ahead, the development of new telescope capabilities will open new windows on the outer solar system. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, roughly 4 times the aperture of the largest current ground-based telescopes. Its combination of light-collecting power and adaptive optics, which corrects for the blurring effect of Earth's atmosphere in real time, will allow direct imaging of Kuiper Belt objects with enough spatial resolution to see surface features on the largest ones. We may be able to map the surfaces of Pluto-sized Kuiper Belt bodies from the ground without requiring a spacecraft visit. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct wide-field infrared surveys from space. Its capabilities for detecting faint solar system objects in the infrared complement Rubin's optical survey in ways that could be particularly valuable for characterizing the thermal properties of outer solar system objects. The infrared brightness of an object tells you its temperature, and the temperature tells you about its albedo, how reflective its surface is. Albedo measurements from Roman could provide size estimates for thousands of Kuiper Belt objects that are too faint to measure directly. Further into the future, a proposed mission concept called the Interstellar Probe has been studied in detail by a large scientific team. This concept envisions launching a spacecraft on the most powerful available rocket with a solar gravity assist maneuver to accelerate it to speeds much higher than any previous spacecraft and sending it on a trajectory that takes it through the Kuiper Belt, the inner Oort cloud, and eventually into interstellar space. The science return from such a mission would be extraordinary direct in-situ measurements of dust, plasma, and neutral gas throughout the heliosphere, extending the in-situ record far beyond what Voyager 1 and 2 have provided. For the Kuiper Belt specifically, the mission would transit the outer belt and potentially the outer population at distances of 50 to 100 astronomical units, directly measuring the properties of the interplanetary medium in that unexplored region. The funding for such a mission has not been secured, and the timeline is measured in decades, even in optimistic scenarios. But the scientific motivation is compelling, and the interstellar probe concept has received favorable assessment in NASA's strategic planning processes. Whether and when it becomes a real mission depends on the priorities and resources of the space science community over the coming decades. What the Kuiper Belt has ultimately done, across the 3 decades since its discovery, is demonstrate that proximity is not the same as familiarity. The outer solar system is close enough to reach with spacecraft that were built with 1980s technology. It is close enough to study with ground-based telescopes that existed before most people who work on this subject were born. And yet it has continued to yield fundamental surprises, revealing new classes of object, new physical phenomena, and new mysteries with every advance in observational capability. This should be humbling and exhilarating in equal measure. If the outer reaches of our own solar system, a region that has been known to exist for decades and that multiple spacecraft have transited, can still hold undiscovered belts, impossible rings, and evidence for hidden planets, then the amount of discovery that awaits in the rest of the universe is essentially unlimited. The universe is not running out of new things to show us. We are simply improving our ability to see. The Kuiper Belt is a reminder that exploration is not finished. It is not approaching its end. Every generation of scientists who look carefully at the sky finds things that the previous generation did not expect and could not predict. The generation currently active in outer solar system science has found more in 30 years than was found in the preceding history of planetary astronomy. The next generation, with better instruments and more data and new theoretical frameworks developed from the anomalies we are currently cataloging, will find more still. The question of what exactly is hiding in the outer solar system, whether it is a planet 5 times the mass of Earth, or the captured remnant of another star's planetary system, or simply more of the complex icy world population we have been slowly cataloging, will be answered. The answer may take 10 years. It may take 25. But the tools to find it are either already built or under construction, and the scientists motivated to use those tools are actively doing so. The outer solar system is not a place to end a story. It is a place to begin one. And by every measure, we have the density of unresolved anomalies, the rate of unexpected discoveries, the improving capability of our instruments. That story is only getting started.